All right, everyone. It's time for our next presentation by Natalie Silvanovich about how to hack a Shannon baseband from a phone.
Hi, everyone. Thanks so much for coming. Today I'm going to talk about how to hack Shannon Baseband from a phone. I'm Natalie Silvanovich, and I'm a team lead on Project Zero. And lately, this fall, we started talking a bit about baseband. We knew that there were baseband vulnerabilities and baseband exploits, but no one on our team really knew how they worked or how hard they were to exploit or what you could really do with them once you found one. So we decided to do what we called a baseband hackathon. We had 5 people on Project Zero get together for about 2 months and just work on baseband and see what we could find. We decided to look at one of Google's own phones, the Pixel 7, and it uses a baseband made by Samsung, the Shannon G5300. And of course, when you think about baseband, the first thing we thought about was, how do we get a software-defined radio? And we did manage to get access to one in case of emergency, but we found, once we started playing with it and thinking about it, it was kind of beyond our skill set as beginners. And also, there's a big difference between people saying, come use my SDR anytime, and actually being available when it comes time to use it. So we ended up not using any SDR. The other limitation we had is there are a lot of baseband attacks that involve compromising the network. Owning the carrier or being the carrier and sending data to the phone that way. We decided that we didn't want to pursue that avenue either. Instead, like in this bad clip art, we wanted to emulate an attacker who was somewhere on the network or somewhere with proximity to the victim phone and reach in and grab whatever their data is without having any special access. So a lot of people worked on this team, on this project. All the people listed here, so I didn't do this research alone at all. It took every one of us to push up this little baby of our first baseband exploit and get it running. So thanks so much to everyone. So to start off, how does a cellular network look like? This is a very, very basic network diagram. You've got 2 people with phones, the caller and the one that's called your phone. And when you make a call, it will either go all the way through GSM networks or it will go over the internet and connect this call. Typically, when people think about baseband attacks, they think about an attacker who is here. And this is kind of where our thinking started. We imagined, what if we were an attacker with some sort of proximity to the victim device? We had our laptop or our fake base station or whatever, and we tried to manipulate the protocols that way. We looked at the attack surface, and it was kind of limited. So most modern cellular standards, 3G plus, they require some sort of authentication with the baseband. So you can't just easily pretend to be a tower and access all the good protocols that might be buggy. So one option we had was to look at 2G for bugs. But this is a smaller attack surface, and we found a small number of bugs in this, but nothing super exciting. The other possibility is ASN1 is a protocol that's used by a lot of mobile devices and mobile protocols. And we did fuzz it, but we didn't find any bugs in it. And when I wrote up these slides, I thought, maybe it's because it's old news, it's picked over, maybe all the bugs are gone. Then 2 weeks ago, I went to OffensiveCon, and someone gave a talk about all the bugs he had found in ASN1. asked him about it, and he told me it was because he had found the very last bug, and they were all gone now, and there are absolutely no more bugs in this attack surface. Anyhow, we didn't find any, and besides, we would have had to get it an SDR and get it working to reach it anyhow. So the other possibility, which I already said we aren't going to pursue, is there are a lot of potential bugs if you compromise a cellular network. But that was kind of outside of our capabilities. So I started thinking about this attack scenario. What if, instead of being in physical proximity, what if the attacker is the caller? I wonder if there were potential bugs there. And where this idea came from is I've spent a lot of time in the past working on WebRTC. And just to give a quick overview, WebRTC is basically the library, the protocol that runs all video conferencing on the web and mobile devices. There is a big open source libWebRTC, which is used by tons of applications, and even products that use alternate libraries like FaceTime and WhatsApp. Their libraries are very WebRTC-like. Basically, all video conferencing works like this diagram. So you start off and you have two nodes that want to call each other. And they have some way that they can communicate securely. This might be over a message, it might be over WebSockets, any way they can communicate. And they do what's called signaling in something called Session Description Protocol. So this is a text format, and it will contain the keys they're going to use to encrypt their peer-to-peer connection. It'll include the codec they're going to use. And it also includes information like their IP address so that they can find each other on the network. Then when they're done doing this, they talk to each other peer-to-peer, either directly using sockets or using stun-in-turn servers. And this is actually a really good attack surface, because not only is there a huge number of rich protocols, but also this is encrypted, so typically these intermediary servers can't do much to verify it. And I found out that this infrastructure is actually very similar to VoLTE. If you think back to that diagram where the call goes over the internet, it actually does work pretty much like this, where the two nodes exchange information through intermediaries, and then they start streaming. And many, many bugs have been reported in WebRTC, so why not VoLTE? You might remember this WhatsApp 0-day that was found in the wild now about 4 years ago. And I know I have probably used this slide in every presentation I've given in the past 4 years, but that's because this was so remarkable. It completely changed how I thought about fully remote vulnerabilities. And this was a situation where real attackers in the wild compromised WhatsApp users by basically making repeated phone calls. And the way this worked is they basically found a bug in one of the protocols and found a way to make it accessible before the call got picked up. And then this allowed them to exploit a bug and get access to WhatsApp on those phones. And this just shows that that very much is a possibility for real attackers. Also, in 2022, I spent a lot of time looking at WebRTC on Android applications. I found a bug and I exploited it, and I showed it works on Signal, it works on Google Duo, it works on a lot of other applications. So that's just another indication that I thought this really was possible. So then, if we're looking at it from this direction, what protocols are available? Well, it kind of depends on what phone you're using and what baseband you're using. But on a high level, the protocols you start with is SIP. And SIP is Session Initiation Protocol. And this is used to connect the session on the two phones. This will always have an intermediary server, and it's the first layer. And then this is used to, like in WebRTC, exchange Session Description Protocol, which has all the peer-to-peer networking information for the two devices that are calling each other. Then once they connect, there will be RTP, Real-Time Transport Protocol, and that is the protocol that encapsulates the codec. And in this case, on most phones, that codec is H.264. So all these protocols are potentially available over baseband, though I have the asterisk, your user space may vary. For some phones, every single one of these will be in baseband. For some phones, almost all of them will be in user space. So you got to look at your phone, figure out what they are. But regardless of whether they're in the modem or in user space, no doubt they are all very complex protocols that make great attack surface. So to start off, to figure out how these protocols worked in the pixel baseband, I dumped it using a core dump. I'm not going to talk about this because this talk, A Walk with Shannon by Amat Kama, has basically all the information you need. So if you want to figure out how to do a core dump and load it into IDA, I'd recommend you just watch that presentation or look at the slides. And what this will basically give you is a core dump that is the whole memory space. And then if you put that into IDA, there's all the code sections, and you can start looking at the code in IDA. And then it was fairly easy to locate SIP and SDP in this baseband processor based on strings because they're string formats. It was also very clear based on this that RTP was done in baseband. I'm still looking at it, and I didn't make as much progress on it as the other protocols, but certainly on Pixel, this is done in the baseband, not in user space. The execution flow was unclear. What was kind of challenging about this is you get this, and it is this huge blob of code, and there's like 4 protocol parsers for this and 3 protocol parsers for that. And figuring out what was actually used was hard. We did not at this point have basically any debugging other than crash dumps. So our first step really was finding a bug and making it crash. This took a while, and once we did this, we had a lot more visibility into the phone. But unfortunately, I think one thing that makes this research hard and not as accessible as it could be is that to even like start debugging, start looking at code, we needed this one bug, this one crash to get going. So crash dumps, I've talked about them. They are awesome. To do a crash dump anytime, use this code on your phone, type it, and it will bring up a screen. So on a Pixel phone, you'll need to root your phone and call set-enforce 0 to turn off SC Linux. Someone told me that on Samsung phones, this is actually the reverse, that you cannot be rooted or else root detection will happen. But anyhow, on most phones that use Shannon, this will work, and then there's just a button that will give you core dump functionality, and it will also let you copy them to different locations if you want to get them off your phone. So then the dump is a tar file, you untar it, and then one file in there will be this dump that you can just load at this address 4000. It also includes like a lot of other super cool stuff, but I'll talk a bit more about that later. One thing I noticed was that if you look at this core dump, it has a bit of the log in it. So if you call strings on it and you've crashed, it will have the registers in there, which is good for debugging. Because unfortunately, on the Pixel, we were unable to get logging working at all. So we were kind of blind as we tested this. There are tools if you do this on a Samsung phone. There is an open source tool called SCAT. There's also some leaked Samsung tools that will work on a Samsung device, but none of this worked. So even though we could see log entries in the code, we weren't able to see the log output. Yeah, once we got the code exec working, it really helped, and we were able to look at a lot more of this. So then, how do we know which bugs can practically be reached? And this is kind of iteration 2 of this question. Question 1 is, how do we know if anyone is using the code at all? And this one, unfortunately, our best answer was either find a bug, make it crash, or if you have code execution already, you can replace instructions with the undefined instruction and then call it and see if it crashes with that undefined instruction or not. But then there's kind of question number 2, which is, let's say you're doing this over a cellular network, because the setup here is that I, as the attacker, need to go through the cellular network. how do I know that they're going to let this bad protocol through their servers? And this is kind of a complicated question. Of course, you can always just try and see if you get kicked off your cellular network or not. But it's good to have kind of a level of thinking about it so that you can think about, what sort of bugs you might be able to get through and what sort of bugs you might not be able to get through. To start with, what protocols are filtered by intermediary servers at all, or processed by intermediary servers? Because people always talk about filtering when they talk about this stuff, but it's not always clear that that is true. The way that cellular networks work is that a lot of protocols need to be parsed by the intermediary. So, if you send them a bug, they could be filtering, or it could just be that they actually need to parse it and their parser can't handle that case. But regardless, this makes it harder to get to your bug. And some of these protocols will kind of be highly processed by servers. SIP is definitely the most on the scale because SIP fundamentally requires an intermediary server. It also needs to be parsed for the connection to actually work. So SIP is parsed a lot. SDP is usually parsed by intermediary servers on VoLTE. This is actually different than WebRTC. This won't happen on WebRTC. But I noticed that most intermediary servers, for a variety of reasons, would end up parsing this. There are other protocols that are less processed. RTP, there is, depending on what sort of setup you have on your cellular, depending on whether you're using Wi-Fi calling or whether you're using cellular, there can be an intermediary server that processes RTP, but it usually doesn't unwrap it. Usually it's just, it will just send it on without processing it. And then there's the codec H.264, and that one is typically not processed by servers. So one thing that was unfortunate is, there's these highly processed, highly filtered ones, and then there's these ones that are probably not processed. And unfortunately, there's no overlap between the less processed and the zero-click bugs. Either you can find bugs in SIP and SDP and you have to deal with filtering and they're zero-click, or you can find bugs in RTP or H.264, and those ones are not filtered, but they're also typically one-click unless you find a bug that makes them zero-click. So that was unfortunate. So we decided to focus on the zero-click protocols with the understanding that carrier networks would probably filter them. So let's look at an example of SDP just to think more about how filtering works. So this SDP has the M line of audio, and that says what is the format of audio. There's also, different ports so that they can have more than one stream, that sort of thing. And let's pretend we have a server here that is processing it. Typically, the server is going to put it into some sort of data structure. Servers are often in Java. I'm going to pretend this one's in C, but it doesn't really matter. It's the same concept. So for M lines, this one is M equals audio, but there's only 3 values you can have there. Audio, video, data. I only have 2 in my enum. But that one, you can think, will almost always be an enum on every single implementation, because why would you bother storing that string when there's only 2 or 3 possible values? So let's imagine on this server it gets stored as a 0. Then there's this port, and the port is an integer, so let's say it's stored as an integer. And then we have the format type. And format types, there's a lot more possibilities. There might be, 10 or more protocols that are supported. And some implementations, this can still be an enum, but some of them, they'll just store the string. So let's imagine in this implementation, they do store the string. Then there's kind of a limit of what sort of bugs are going to make it through this server. Like, imagine there's a bug where you're making this audio a really long string. That's obviously not going to make it through the server because it's going to either cause an error or it's going to make the enum 1 or 0, but you're never going to get that AAA string back when it re-encodes. Meanwhile, if you put a long string in this format type, depending on the server implementation, maybe you will get it back. So this is just like a way to think about it, that if you look at the specification and it's like a string with lots of different values, maybe that's a good candidate. Meanwhile, if it's like a number with 2 possible values, maybe that's not a good candidate for a bug that'll actually get through the server. So with this in mind, we did code review. As I said, bugs are still possible if your malformed data can be decoded and re-encoded. A general observation is that servers tend to be less sensitive to malformed SDP versus SIP. That's because the servers actually need the SIP to connect. Meanwhile, SDP, sometimes it's okay if it's bad. The other thing to know about SDP is that your phone will often remember your last good connection. So let's say your SDP is so malformed the connection can't work. Usually if you make a call from that number with the correct SDP, the person doesn't have to pick it up, but if you just hang up and then do it with the malformed one, usually that connection will still work because the phone will remember. So that's like a nice little trick. Also, this filtering did vary a lot across carriers. And the other thing to keep in mind for later is, because these are text protocols, they also had reserved characters. So, if I had a bug with, 00 in it, or /A or /D, you can't do that because that's part of the protocol and will change what it means. So another thing we did is we had this unicorn emulator from a training we did with Marius Mensch and Dominic Meyer, and they gave us this unicorn emulator that would work on Shannon basebands, and we loaded up our Shannon baseband in it. And this is an emulator that doesn't have full OS features, so you can just emulate a single function. But this was another way that we tested that our bugs were real. Because you could call the function with, for example, a malformed SDP, and this wouldn't guarantee that it would make it through the carrier, but it did guarantee that at least you weren't confused and this bug was a real bug on the software. And we were also able to test and fuzz features, free from carrier interference, so we didn't have to worry about if we started fuzzing, we get a call from the carrier one day being like, hey, what are you doing? So that was nice. So based on the code review and the fuzzing, we found quite a few SDP and SIP bugs. I'm going to give an example of some representative bugs here. So this was the first bug we found. This was the one that allowed us to crash the baseband and know for the first time that we were really hitting the code. But here's the problem. So in SDP, there's this one format, accept types, that has the different formats that's accepted in the call. And these strings are stored as a string array by the baseband, but it's a fixed size 12. So it turned out that this would overflow the array with stood strings, and the sample of the bug is below. So if you had an accept type that was really, really long, this would corrupt memory and lead to a crash. And like most of these bugs, this was fixed March 6 of 2023. And then there was a similar bug we found. This is the chat room attribute, and it's the same idea. The array had a fixed length of 12, and if you have more strings in the array, then it overflows. There was also this bug. This is another SDP bug involving the configuration attributes. And this one had some nice properties. So this array, for whatever reason, was fixed length 14. But instead of copying strings, this would actually call ASCII to int on these numbers and copy them as bytes. So that was nice. This had no character restrictions. It could copy from any value from 0 to 255 over this 14-byte array and basically go out of bounds as far as you wanted as well. So this is kind of a cool bug. And finally, there was this bug, and this I just want to give as an example of one that probably won't make it through the carrier network. So there's this format protocol in SDP, and the first parameter is an integer. And there was this bug in the Shannon parser where in the intermediate processing, it would copy this assuming it was an integer, even though it hadn't checked that it was an integer. And you could just, it was an overflow in string copy. And this would have been a cool bug, except almost all of the intermediate parsers in the carrier networks would notice this was not an integer right away and just reject the packet. So, there might be a carrier somewhere where this works, but we couldn't find one easily. And finally, I want to give an example of the sort of SIP bugs we found. And the SIP bugs were also, way less reliable on carrier networks because the SIP was required for functionality. But this one is similar to that bug I just showed you, where they would assume it was an integer, this long AAA string, but it was actually not, and then it would be a big buffer overflow. Thankfully, most networks won't accept this, but we did find about 7 bugs like this. Yvonne Fratrick found most of them, and they were all fixed on April 10th, 2023. But yeah, this turned out to be quite a buggy interface, and through fuzzing and code review, Yvonne found quite a few bugs. So now that we had some bugs, how do we actually test them in real life on the carrier network? So I went through my collection of mobile devices, which is quite vast at this point, and found one where this functionality happens in user space. And I found on the Samsung Galaxy S9, SDP and SIP are processed in user land, and they use a library called REcip, which is open source, and I'd actually looked at before, so it was pretty clear quite quickly where the SIP and SDP processing was. So I was able to use Frida, which, if you haven't used this awesome tool, it is an awesome tool that allows you to hook functions using JavaScript on a mobile device or a desktop, and write JavaScript that changes what they do. And in this case, I was able to just swap out the SDP or SIP being sent and try this bug on all sorts of devices. We found that the filtering was different for different carriers. Some of them let all of the bugs through, some of them let almost none of the bugs through. The other thing was that caller carrier was the most important, which is actually positive for an attacker, because the attacker picks which carrier they use. But typically, it was the caller carrier that would decide, no, you can't do that with your SIP, and usually the callee carrier would accept the SIP except in extreme cases. And the 3 SDP bugs work fully remote. I would say on most carriers, there was the odd carrier where 1 or 2 wouldn't work, but most carriers accepted at least one of these bugs. So now let's think about exploitation. And I'm going to review, before we start, what these 3 bugs actually do from an exploit perspective. So we had the chat room and the accept types bugs. And those both overflowed a fixed heap buffer. It was 12 strings, which I think ended up being 120 bytes. And that size is not controllable on the heap. The allocation will always be 120 bytes. What you can control is it's overflown with standard strings. You can control how many standard strings that it's overridden with, and you can control the contents of those strings. Then there was this other bug, which was the configuration one. And this one had a 14-byte buffer, and that was a fixed size. You could overflow it as much as you wanted with whatever values you wanted, and this one was byte-wise. But you can't control the allocation size. You can only control the overflow. So also, for exploitation, what are the security features of this baseband? So there was no ASLR, which was a bit surprising. There were stat cookies, and the stat cookies change value on every reset. And this is a good security feature. Unfortunately, we didn't find any stack overflows, so it wasn't really relevant. There is a limited heap corruption detection. The way this actually worked was there was a heap cookie, but the heap cookie always had a set value, which is A. And if it got corrupted in the normal heap mode, it returns. So for exploitation, this was actually pretty good. There were some situations where it was a barrier, but in most situations, it would let us mess up the heap, and if we got it wrong, we could try again, and we could try again, and we could try again without it crashing. So I would say this feature probably helps exploit writers more than it hurts them. That was certainly the case with us. And then there was a non-executable stack and heap, which was a bit of a barrier because when we were doing this, I looked at like all the information about baseband exploits that I could find, and they all did not deal with this. There's some talks where they say like, oh, there's read, write, execute sections. There are not any more of these in the Shannon we looked at. They'd all been made either read, write, or read, execute. So that was one security feature. So now let's look at what a Shannon heap chunk looks like since we were corrupting the heap. And there's kind of a few interesting features. There is the heap ID. And that is actually an inline number that tells the heap what algorithm was used to allocate this chunk. And then I've already mentioned there is this cookie that basically makes the heap more stable by not freeing corrupted chunks. And then the rest of this is unfortunately a slab allocator, which was a problem. So a slab allocator is a heap algorithm where there's pretty much no heap header in line with the chunks. You know, the chunks will be adjacent through all the allocations, and typically the only way you can exploit a slab allocator is that you get an object allocated in the heap, and then you overflow that object and hope you can find one that has the right pointers or whatever to use for exploitation. I have tried to exploit slab allocators in a fully remote context a lot of times. I have never really had any success with it. You see a lot of this stuff in browser exploits, in other types of exploits, where you have a lot of heap control. But the problem with a fully remote exploit is you kind of don't. It's harder to find in something that's not a browser the right object, and it's harder to find primitives you can use to allocate objects over and over, and it's harder to find other types of primitives that control the heap. And then there's also the problem that, you know, you're usually not the only thing going on. So, you know, you might receive packets from someone else. Lots of things can be happening that you don't control and you have no way to detect. So I'll say I have never succeeded in exploiting a slab allocator on a fully remote context. I've found the best way to handle this is to make sure that the thing that your overflow is exploiting is happening as soon as possible after the overflow. Reducing that distance in terms of execution time, I think, will make your exploit more reliable than anything else. So at this point, I was like, oh, you know, this probably isn't going to work. But then, wait a sec, what is this heap ID? And it turns out that this inline indicator of heap type is actually the only thing the heap does to decide what algorithm to use. You know, it doesn't check, you know, address boundaries. So if you overwrite this value, you can just use a different algorithm to free this chunk. And one of these algorithms was called heap6. That's because it's ID 6. And this is quite a bit like the Linux allocator. It's a linked heap allocator that did not have unsafe unlinking. So in this allocator, this is what the free algorithm looked like. And this had a lot of like super good qualities. Yeah, to start off, you had no unsafe unlinking. So if you manage to overwrite a header, you'll overwrite one address with the other address and vice versa. So that's an arbitrary overwrite. But also, look at how they get the header. The location of the header is based on an offset pulled out of the current memory chunk. So that is also super good. Because sometimes you have this problem in exploits where it's like you need something at an offset, but you also need a different thing at that offset. But this allows you to make this heap header kind of be wherever you want. So you can make it so that it's somewhere convenient within this chunk. So I tried to figure this out. My first attempt was the configuration bug. And this was the one where you could overwrite the 14-byte value with whatever value you wanted. And Of course, I would do this with absolute pointer values. I tried to overwrite this next and previous with absolute pointers. This turned out to be like way harder than I thought it would be. The problem with this is that there's not so many heap chunk sizes on the Samsung baseband, so I think this one ended up being allocated as 32 bytes, which was the smallest size that could be allocated, and there was so much contention. And weirdly, it was actually pretty hard to overwrite an active buffer. So this configuration buffer would get allocated, and then there'd be like something next to it. And I would have thought that the chance that that was active would be really high. It turned out to be really low. And most of the time when I did the overwrite, this would already be a free chunk, and then the heap stuff wouldn't happen. When I tried this, sometimes it would take even 5 to 10 minutes doing this over and over before I hit a chunk that was actually active. So this was not great. This also gives you another problem, which is you've got, your one chance, your one overwrite. Where do you put your shellcode? You either need some like really good ROP, or this isn't good. So I'm gonna like chalk this up to it sort of worked. This bug in particular looked great and didn't quite pan out. So then Yvonne said we should try it with the other bug. And this is the bug where there were the 12 strings, which were 120 bytes, and then this would be rounded up to a chunk size of 256. But what was even nicer was that within this function, there were multiple allocations. And first there would be the array of strings, and then it would allocate each string and put it in the array. And just to give an idea here, so like the way this would be parsed is it would be like, array of 12, and then that's always the same size. But then let's say, this first string is also 128 bytes. That would be guaranteed, or not guaranteed, but very, very likely to be allocated straight after. And then the second one would be very, very likely to be allocated straight after. So this gave a good control of the heap chunks. The bad side of this was there are limits to what can be the value of the overflow, because these are all strings. And this was sometimes good and sometimes bad, but Yvonne figured out kind of a way to shuffle it so that the length of the string and the pointer of the string would overflow this heap in the way that it looked like a header, and it actually worked. So we were basically able to overflow this so that this header, based on the length of a string, would actually make the offset of the free to be inside the contents of the next string, so that that was where the overflow would happen. So I think this is the first attempt, and it was actually, we made the header at this QQQQ location, but because of this offset, you could do this. So then, what next? The Shannon baseband heap, this is actually useful for testing, supports a debug heap and a regular heap, and in that 5096 thing you can type into the keyboard, that'll also let you turn this on and off. But the way this works at the highest level is that there's a static pointer in the system that points to the free algorithm, and we use this bug to overwrite this. And one of the big problems with these heap overwrites is that they go both ways, right? So if you're overwriting B with A, then it will immediately overwrite A with B. And that means that both of the pointers you overwrite have to be writable, which is kind of no fun if you're trying to overwrite a function pointer with something that's actually code, because if it's code, then it's not writable, and then you get a crash. So the way we dealt with this is we wrote it in offsets. So we overwrote this function, just the lower bits, so that it would point back to one of the string buffers, but then the highest byte remained unchanged, so it still looked like a pointer. So then after that, we could point it to a few gadgets that would get us to this gadget, which was at scatterload RT. So if you found this presentation a bit boring and you've nodded off and you're not listening, I would suggest you open your ears at this point, because I think this is the most interesting thing we found and the most useful one. which is Yvonne found this great gadget, which is part of the ARM OS, so it should be on most ARM devices, and it was super, super useful for exploitation. It's at the symbol scatterload RT_2, and what this does is it will take in a heap pointer, and then it will take a pointer out of that heap pointer, then increment, and then take 3 more values out. Then it will call that pointer with the 3 values as parameters, and then it will increment, and then it will do that again and again. So this is a way you can make an exploit call function after function after function from your heap parameters, and yeah, very useful. I would say it only has one downside, which is that it's an ARM, so you might have to do a branch exchange to get here, but anyhow, super cool. This is my favorite gadget ever. So now that we had that, we could call a lot of functions. So now to deal with this pesky non-executable heap. So non-executable memory is controlled by the domain access control register. So we found this gadget, and it needed another gadget, but using the scatterload, you can call the gadget that puts FFFF in R0, then you call the next gadget that calls this, and then this made the domain access register so that there's basically no memory enforcement. So this was kind of bad in one way, in that once you've done this, any out of bounds memory accesses won't cause the data abort, so if you really mess things up, you won't know. But on the flip side, it definitely got this exploit going. So now we've got shellcode. We could execute thumb from the heap. As I said, there's forbidden characters, and this was another annoying thing about carriers. Some carriers had like extra forbidden characters, so sometimes there's more than these, but these are the ones that most carriers have. There is no length limit to the shellcode other than like your carrier will eventually explode, and the one limitation of this stacker thing is that it will only work in the thread that you're in right now. So if you find yourself in a situation where you want to execute code from other threads, what you need to do is overwrite code that's executable. But because there's no memory protection anymore, like you can do that and then just find some unused test function and put the rest of your shell code there. So now what? We wrote what I think is the worst proof of concept ever. You'll see Yvonne is sending a text message that is test, but on the other device it comes as hack. I'll show that again. And that's because we had code execution. But this actually brings us to the eternal question of baseband exploitation, which is, now what? Because this was actually one of our questions in this baseband hackathon. We'd heard so much about baseband exploits, but kind of what are they actually useful for? What would an attacker want to do that they can do with them? And of course, one of them is that you can monitor phone and cellular internet traffic. So there was a talk a long time ago where some people came up with a proxy so you could compromise the baseband and proxy the internet and see where people were browsing. That is certainly a possibility, though SSL will make that harder. And the other thing is that if the person's using Wi-Fi, you won't be able to monitor their internet at all. But still, this is, not a trivial capability, being able to monitor someone's phone call, their SMSs, that sort of thing. But what I've started looking at lately is trying to do privilege escalation through the application processor driver, because that's another possibility. If this is an easy way to root or kernel privileges on your Android device, that would make this a super good fully remote bug. So I've investigated how this has worked a bit. The way the communications processor, the baseband, talks to the application processor is through shared memory It's written by PCI on both ends, and then there's both GPIOs and MSI interrupts that drive this. And this is a fairly large attack surface. I haven't quite found anything yet, but this is going to be my future research. Try and get this so this isn't just a fully remote baseband bug, but a fully remote bug that can get kernel privileges on a pixel. So yeah, finger crossed that I'll figure that out soon. But what did we learn here? So we had 5 people working for 2 months. These were members of Project Zero. So these were people who had a lot of experience exploiting other targets, understanding other targets, who knew a lot about code, but no one really knew anything about baseband. And within 2 months, we had a working fully remote exploit. So that was surprising. I would have thought it might take a bit more effort, but that's kind of where the bar is at. We found it to be a bug-rich environment. I spent a lot of time looking at Android code, looking at iOS code, and I would say this was honestly a bit of a step down, that these bugs were easier to find, more plentiful than most other targets I look at. The lack of tooling was a major barrier. Pretty much what we discovered is that hacking baseband is like hacking an iPhone, right? You need to stay 1 bug behind so that you have your jailbreak so that you can do debugging. But what's different about iOS is that there's a community that does this. Meanwhile, with baseband, we pretty much had to, with no information, come up with our first exploit and get this going. So yeah, this is a major problem. I think if we want to get baseband up to the standard of the rest of the mobile device, this needs to be addressed. There needs to be more transparency, more ability for people to examine and understand the baseband so that we can get rid of these super easy to find bugs. So thank you. I am glad that there is one person who agrees with me here. So fully remote baseband attacks are a possibility. That was maybe something we didn't expect going in. Most baseband attacks you hear about require proximity, but I tried this across continents, I tried this across carriers. This was very much a possibility. Finally, Shannon mitigations have improved, but are still lacking. It was not at a point where I could pull out the exploit from another presentation and use it. They'd added a couple more features that made this more difficult, but it's still not close to what you would find on the application processor of any mobile device. If I had to pick 2 things, I would pick ASLR. That would have made it much harder. We wouldn't be able to hardcode pointers. I'm guessing that this would have moved this from a 2-month project to a 6-month or more project. I think that really would have increased the number of bugs and the amount of effort we needed. I think number 2 would be heap hardening. Heap mitigations aren't supposed to make things easier. So I think that if Samsung added some heap mitigations, that would improve security a lot. So that's it. Thanks a lot. And hopefully we have time for questions.
Hi, great talk. I was just wondering, I don't think you mentioned what your final debugging solution was, if you ever had one.
Our final what?
A debugging solution for debugging
Yeah, so
exploits.
our final debug solution was strings on a core dump, pretty much. And then with code execution, we were able to do stuff like add undefined instructions and do things to figure out execution. But yeah, we never got to the point where we had any actual working debugging.
Gotcha. And then I have one more question, if you don't mind.
Sure.
Did your team ever look into using firmware for? Did your team ever look into using firmware for full system emulation for the Shannon baseband?
Like no, we haven't used that.
All right, just wondering. Thank you.
isn't it a problem that most of the verification happens on the caller side for the carrier and not the callee side? Because what if you have a malicious caller? Seems like it should be the opposite, because you could just pick the one with the least amount of verification.
Yeah, that definitely is a problem. I'm not sure how much I'd want to put the onus on the carrier in the first place, just because there's so many of them and it's not so hard to become a carrier in the first place. But yeah, definitely if carriers want to protect their customers, they need to have it on the incoming caller side as opposed to the caller one, because that doesn't really do anything to prevent attacks. You're right.
Awesome presentation as always, Natalie. Two comments and a question. One comment, I think that you'll find that if you think the baseband is a bug-rich environment, the carrier equipment is going to be a wonderland of fun. Second comment is don't forget Clark's rule of advanced exploit technology, because sufficiently advanced one-click exploits, and I'm doing this to plant a seed in your mind, because sufficiently advanced one-click exploits are indistinguishable from zero-click exploits, reminding you, I don't know if you remember 2 years ago or 3 years ago, at Pwn2Own, they had a bug that was just amazing on a Zoom call where they silently exploited the caller and were able to get code execution without the call actually dropping. So if you do it well enough, it can really not be, the click can be not an impediment. So my the question is, did you look at what brand of radio network that you were connecting to on the carrier versus the filtering? Did you get any kind of correlation about which carriers, switches, or RANs did the filtering and didn't?
Yeah, so actually, I have a comment on your comment first, which is that you're right about the one-click exploit. The other thing to be careful about is bugs that make one-click exploits into zero-click exploits are not uncommon either. You know, for example, with that Zoom bug, sure, you're in the call, but like someone might one day find a bug on, any platform where, they can pick up the call, and then what? So yeah, I agree that, those can be promising attack surfaces, and it's important not to forget about them. Yeah, no, we didn't look into carrier equipment at all. I can't tell you much about the stuff that let our attacks through.
Okay, thank you.
Thought about moving further up the stream and building your own femtocell and monitoring from that point?
Yeah, sorry, can you say that again? I couldn't hear.
Have you ever thought about moving further up the stream and building your own femtocell and monitoring from that point?
I have not. I think that would be a cool idea, but yeah, I think if we started, getting our own equipment, like SDRs or that sort of thing, or creating a femtocell, there would be a lot more possibilities for this type of attack. That's great. I think that's it then. Feel free to contact me if you have any more questions. Thanks a lot.